I want to take us back 48,000 years ago, back to the Stone Age. Back to when people like you and me were just hunter-gatherers. Farming wasn't a thing. Cities were not a thing. We were living day to day, hunting antelope, running from lions, the whole shebang. At this time, healthcare wasn't a thing. There was no Obamacare, there was no hospitals, there was no doctors. To the highest extent, we may have some kind of herbalist. And at this time, in the wild, basically in the wild, the human lifespan was around 33 years old. This is what we can take as our natural lifespan in the wild with no medical attention. And it makes sense. Back then it was a different time, and humans back then didn't live that long, right? It's kind of what we expect from a long time ago. So now let's fast forward around 38,000, let's fast forward around 37,000 years later to medieval England, Victorian England. It's 1800 right now, and advances in germ theory have been made. We have cities now. The Industrial Revolution's underway, and humanity's come pretty far. But in the grand scheme of things, after millennia upon millennia of progress and wars and great empires and all this human progression, we've only increased the human lifespan by about 7 years. Now we're living up to age 40 on average in the most developed country in the world. So what if we took it a little further? Let's take us to 150 years after, 1950s. How far have we made it then? Well, to recap, we put 7 years on the human lifespan in around 40,000 years. But in 150 years, we went from age 40 to be the average age in the developed world to age 65. Nice little increase there. And this was done in 150 years. So we're already seeing this huge spike in basically years added to the human lifespan, and time bought back from death to people like you and me. But we can do better than this. 65 years in the 1950s in the USA. Let's fast forward to right now, 2019. The average human lifespan, for accounting for people of different races and men and women alike, is 78 years old. We've come a long way now. Now it's been around 70 years, and we've added an extra 18 years onto the human lifespan. This has come through democratizing healthcare and making it more accessible for everyone around us, but also from medical science, just breakthroughs in medical science and hygiene theory, and in just socioeconomic balance where people can afford more healthcare. But now we're at this inflection point where medical science seems to be putting us in a position where we can make incredible amounts of change and add incredible amounts of years to the human lifespan, even way beyond what we have currently done so far. So we're in this position right now where we can make kind of adding 17 years to the human lifespan in around 70 years look like the 7 years added to the human lifespan into 40,000. We're at this inflection point. And this is kind of coming with its own caveat that we've been adding time into the human lifespan time and time again. We've been proving death wrong time and time again. The average human lifespan now is 78, when back then it was 33. So we've over doubled our lifespan since modern humans have existed. And this is all kind of coming to a massive realization for all of us. The realization is that aging is not a part of life. Death is not just a part of life. It's not natural. Not natural per se. Not really defined to us. Aging is a disease. And it's a disease that we can fight back on. It's a disease that we can push back. It's time that we can buy back if we just know where to put the work in and the resources in and the time into. And this realization has come with a huge amount of companies that are working to push forward the longevity industry right now. Amazing companies like Unity Biotechnology and all these other firms that are working on these revolutionary technologies. A lot of these technologies, like such as senolytic drugs, working to push forward the human health span by getting rid of some of the biggest factors of aging. And the bedrock of all these biotechnology companies is a new science that's coming out. It's new science that's coming out that's revealing how aging looks like when it's happening live in our bodies as we age. It's profiling what the weaknesses of aging are and what is the Achilles heel of death as it comes towards us. All these titles aren't your average news titles. These are scientific journals. Some of the top scientific journals in the world, like Nature, reporting news like telomerase reverses aging process. if you can get a scientific journal to put a title this incredible and this profound, you know something amazing is happening. And something amazing is happening. Because behind the research and the industry, we're pouring in $17 trillion into a longevity industry that's hoping to yield more time for us on Earth. And one of the key factors of aging that the industry has been obsessing over for the last few years, and if any of you guys do a deep dive into aging, you'll quickly come across this thing. And it's called senescent cells. Senescent cells are probably one of the biggest proponents of physical aging that we've identified to this day. On the high level, a senescent cell is basically our own healthy body cell that has gone into a state where it cannot divide anymore. So our normal healthy cells would divide, but as a mechanism against genomic damage that the cell has incurred over time, this once healthy adult cell of ours becomes senescent. It stops growing and just kind of sits in a still idle position. And while it's doing so, it's also releasing chemicals into the bloodstream, into the extracellular environment. Now, normally this is not that bad. This is actually our body's defense mechanism against the cell accidentally killing itself or becoming cancerous because of genomic errors. And our body is actually really good at systematically clearing these cells with our immune system. The issue comes up that as we age, our immune system is less capable. That is why old people, as you get older, people tend to get sicker. And for the same reason why older people get sicker, older people are actually not as good as clearing senescent cells as younger people like me. And then what this results in is something called chronic senescent cells. Senescent cells keep occurring, and our immune systems are not as good as clearing them. And what happens is that we just get this immense buildup of these senescent cells. And with this immense buildup of senescent cells, we get the immense buildup of these cytokines, these microvesicles, and all these different proteins that the senescent cells release into the body. Now, the release of these chemicals has to have an effect, and it has. Studies have shown that these chemicals, when they're released into the bloodstream, have a direct correlation with with a lot of key age-related diseases like osteoporosis, atherosclerosis, and a lot of signs of early onset of cancer. So we have these senescent cells that have been proven to be one of the biggest proponents of aging, not only in humans, but in mice and in other mammals as well. And we have an immune system that slowly fails us as we age, and fails us at clearing these cells that are not wanted. So this also got scientists thinking too. Scientists decided to clear out senescent cells systematically from mice back in 2011. And these researchers at Mayo Clinic injected the mice with a drug. And the purpose of this drug was to clear out a specific type of senescent cell within the mice's body. And this drug would be injected into the mice starting at age 3 weeks, and it would be injected once every 3 days after that. And they'll be targeting adipocyte senescent cells, so one type of senescent cell. And the picture up here just shows us the very stark difference, where you have one mice on the right who was treated with the medicine, the drug to kill senescent cells, and then a mice on the left who is a control group who has not had any senescent cell clearance, and they're just aging like a normal mouse. Now, behind this picture, what we see is that these mice stop having one of the chronic effects of senescent cells, which is the buildup of plaques in the artery. So that negative effect of senescent cells has been effectively reversed in this mice. Not only that, these mice are more physically capable and have greater fat stores, the ones who were treated, compared to the mice who were not treated and just aged naturally. And not only that, by the time these mice aged, and by the time the treated mice aged to the point of their death, they had actually lived around 30%, on average around 30% longer than the mice who weren't treated. They had not only lived 30% longer, but they also lived 30% longer at the same health capability. So if we would put this in human terms, a 110-year-old human being treated with this disease, with this senescent cell killing drug, who was supposed to die at age 120, would be just as healthy as an 80-year-old who wasn't treated, who was set to die at age 90. So you have this translation of a healthy time period in a longer lifespan. So this is what we mean by increasing the lifespan by 30%, while also keeping the same health span. The implication of this is that if we can realize this vision of clearing senescent cells from the body, If we take this 78-year average human lifespan and apply the same rate of change that we saw in the mice, which is optimistic, of course, but if we apply the same roughly 17 to 35% rate of change in the lifespan, we're looking at around a 91 to 105 year lifespan in North America. Approximately around 20 years added onto our lives. This isn't normal, because this is one proponent of aging that we've identified that we can clear out, and that we know how to clear out with these drugs that can kill senescent cells. So this got me thinking, like, how do we level up the human immune system, the system that naturally is supposed to get rid of senescent cells? How do we level this up to get rid of these senescent cells and add the 20 years into our lifespan, just using systems that are already in place in our bodies? And this is what led me down this project, which I'm really excited to present today, called Senescent Antigen Receptor T Cells, or Sar T Cells for short. On a really high level, Sar T Cells takes a type of human immune cell called the CD8 T cell. Now, the primary job of a CD8 T cell is to fight unwanted cells and kill them. And this T cell has been paramount in creating a lot of new immunotherapies. And likewise, we can break down our own immunotherapy, Sar T cells, into three main parts. The outcome we want, which is killing the senescent cells, which would be taking T cell mechanisms and killing senescent cells. The engineering part, what would we be doing differently to the T cell to make it kill senescent cells instead of its natural targets. And then the pipeline, the clinical pipeline, how would we plan to get Sar T cells from the lab and from the engineering bay into the patient bedside and getting people to live longer. So naturally, in our bodies, T cells are kind of like the elite special forces of our immune system. If you can imagine the immune system like an army that we have, T cells are like a special forces wing. Their job is to kill unwanted cells. And they do so with this kind of tracking system. So on the surface of the T cell, you have a special receptor. The receptor of this T cell is like your arms and your nose if you were blindfolded. This receptor allows the T cell to locate, hone in, and bind to an enemy or unwanted cell in our body, which the T cell will then kill. So the main job of the T cell is to take in an input of an antigen, which is basically a fingerprint of a pathogen. It's a chemical fingerprint found on the surface of a diseased cell. Is to take that antigen, bind to it, and then kill the thing with the antigen on it. So as you see right here, with the Sar T cell, what we're doing is that we're engineering a receptor, a man-made receptor on the T cell, so that it can target specific antigens for senescent cells. So if we can detect a molecular fingerprint for a senescent cell, we can then program a T cell into a Sar T cell to make it kill senescent cells in the human body. So then once this Sar T cell would bind to a senescent cell antigen, its job would then to be release these proteins, basically, called cytotoxic granules. These proteins would then cause the senescent cell to die by a natural process which our body can handle en masse, called apoptosis. Now the amazing thing about this is that it's a relatively simplistic process from a biological perspective. And it's something our body does naturally all the time. So when I was designing this experiment and this project idea, I wanted to use a lot of the existing infrastructure that has been done with T cell immunotherapies, specifically with CAR T cell therapies. And this proved very useful when we actually built out the plan to build this Sar T cell. So ultimately, what we care most about when it comes to Sar T cells is the receptor. This is what makes the Sar T cell unique. The Sar T cell is just taking the same cytotoxic killing mechanism of a T cell, but with a new receptor. And specifically speaking, we're looking at the single chain fragment variable of the receptor. So this little top part of the receptor. This is the part that we want to specifically engineer because this is the part that uniquely binds to the antigen. In every body, each unique antigen binds to one unique receptor. And in our man-made receptor, the single chain fragment variable is what's going to bind to the antigen. So we want to make the single chain fragment variable special for whatever special antigen that we choose. The process of this is actually using a lot of the existing techniques, which allows us to cut down on a lot of cost and price. Namely, some classic biotechnology techniques like hybridoma allows us to create a specialized single chain fragment variable, or scFv, from the antigen that we're choosing. So on a high level, we can inject the target antigen of the senescent cell into a mouse, and we can utilize the mouse's immune response to that antigen, almost like a vaccine response to that antigen, to produce a special type of antibody-producing cell called a plasma cell. And when we combine them with a tumor cell to get these plasma cells into a hybrid, basically these hybrid cells have a very long lifespan of the tumor cell, but they also produce antibodies en masse. So we're kind of producing, on a high level, these like immortal antibody-producing factories, which we can then procure into a single-chain fragment variable using another technique called phage display. So we can grab this antibody from the hybridoma process. We can sequence the genes for two very specific parts, shown in the pink and the purple, the VH and the VL parts. We can put it through the process of phage display and yield the special receptor part that we need to bind to senescent cell antigens. And once we have that, we have our full Sar T cell. We have our full Sar T cell product ready to go. And the vision for this is that we would use the existing adoptive self-transfer pipeline, which is currently used for CAR T cells. We would basically apply the same process into Sar T cells, so we have a relatively lower barrier to entry when it comes to spreading this product and making it a reality. So by taking the existing mechanisms that we know and the existing processes that we have, I laid out the groundwork for the first prototype of Sar T cells. This is the first step of what potentially getting rid of senescent cells in the body looks like. So Sar T version 0.1 aims to target a special type of experimental design, where it aims to target a special type of fibroblast senescent cell called IMR90. IMR90 is a fetal lung tissue that we would generate from stem cells in a dish, and then target with these senescent cell killing T cells. So with IMR90, we've found a couple of target antigens, which are specific for IMR90, which is good. This allows us to prevent any side effects that would theoretically arise in the body if you were to inject it. So our primary target would be SCAMP4, which is a surface protein, and we also have some co-stimulatory antigens, which basically means these can serve as kind of side receptors, which act as a check and balance for our Sar T cell, which are basically safety features, just in case that the Sar T cell picks up on a false positive. These other antigens would need to be triggered in order for the Sar T cell to kill whatever cell it's binding to. This is a common practice in the CAR T cell industry, where you design multiple receptors to make sure you don't get autoimmunity or a T cell killing a person's healthy cells. So this is the first proposal that we have. And in the grand scheme of things, our timeline is looking like this. So starting in October 29, which is when the project was birthed out, we basically organized a database of viable antigens to be used, including SCAMP4, which I mentioned, and we laid down the fundamentals for the product, and then we submitted to CES. Now, within the next 7 months, the plan would be to build out a formal research experiment. We'd be building out a full-on white paper with design methods and experiments to then get it peer-reviewed and published. And then from there, over the next 12 months, we'll be actually reviewing the experiment design and trying to get it with a journal in order to fully flesh out this idea, as well as getting this idea into a developmental immunology lab and testing Sar T version 0.1 on the IMR90 cell cultures. If this 1 year timeline is realized, we may be looking at yielding one of the first immunotherapies to actively combat aging, and a novel immunotherapy to actively destroy senescent cells in our bodies using a methodology that our body already uses to kill unwanted cells. Taking this back 38,000 years ago, I don't think anyone would have fathomed that we'd be at this point right now, where at one point it took us millennia upon millennia just to add 7 years into our lifespan. And then suddenly it was like 70 years to add 17 years into our lifespan. And now we may be looking at around 1 or 2 or 5 years to add an extra 20 years into our lifespan. This may be the showing of a kind of a Moore's Law kind of trend we're seeing with biotech, and especially with longevity and lifespan added. And honestly, if you asked me how long do you think I'm going to live, I probably couldn't give you a solid answer. And I can say that with a confident smile. So if you can join us in supporting this project, maybe, just maybe, we can buy back some crucial years lost to aging.